Enterprise AI security works best as a layered system. Identity, applications, models, data, monitoring, and response all need clear controls. In this section, we'll map those controls to the architecture, so gaps become visible and priorities become easier to set. We've already defined the AI security stack: identity, infrastructure, applications, data, models, monitoring, and governance. Now we move from naming those domains to placing real controls in the right layers. That mapping makes the architecture usable for risk modeling and prioritization. Layer mapping means placing each control where it can actually reduce risk. Identity checks belong near users and apps. API protections sit at service boundaries. Model guardrails surround prompts, responses, and AI service calls. Data controls protect storage and retrieval. Monitoring and response connect the layers. The key is ownership. Every layer needs prevention, detection, response, and governance, so gaps are visible before they become incidents. Human access controls should work as a chain, not as isolated tools. SSO provides one governed entry point and stronger audit visibility. MFA adds proof that the user is really present, especially for AI workbenches, admin portals, and data platforms. Conditional access checks context, such as device health, location, and behavior. Role-based controls and privileged access management then limit what users can do, so access matches need, not convenience. In enterprise AI, many important users are not people. Applications, pipelines, APIs, vector stores, and model providers act through service or workload identities. The goal is to avoid permanent keys scattered across the environment. Prefer managed identities, OAuth client credentials, and short-lived tokens issued just in time. Scope each identity narrowly: which service it can call, which dataset it can read, and which operation it can perform. Vault secrets, rotate credentials, and review access regularly. At the application and API layer, every request should be treated as untrusted until it is verified. The API gateway confirms identity, checks permissions, validates request structure, and limits abuse through throttling. Web firewalls and application filters look for malicious payloads, prompt injection patterns, and abnormal traffic. Secure session controls protect tokens and prevent unauthorized continuation. Only after these checks should prompts, tool calls, and integrations reach AI services or sensitive data. Authorization is where identity becomes enforceable policy. It answers not just who are you, but what are you allowed to do. Controls should check user, role, tenant, data scope, and action. Rate limits reduce scraping, cost spikes, and denial of wallet attacks. WAF rules filter known exploits, suspicious payloads, and bot-like behavior. Monitoring ties these signals together, using request patterns, prompt anomalies, errors, and latency to detect abuse that individual controls may miss. Think of the application layer as the point where user intent becomes action. Before that action reaches models, retrieval systems, or tools, it should pass through a secure gateway. The gateway enforces allowed APIs, validates tool calls, filters sensitive outbound data, and applies policy controls. Responses need handling too. Check outputs, limit unsafe content, and fail safely when trust boundaries or permissions are unclear. Model guardrails act as checkpoints around every model interaction. Before a prompt reaches the model, input filters look for prompt injection, policy violations, and sensitive data. Retrieval and model calls are constrained by enterprise rules about what data can be used and how responses should behave. Before anything returns to the user, output filters catch unsafe, restricted, or confidential content. Telemetry closes the loop, helping teams tune controls based on real incidents. RAG security does not happen only at the model boundary. It starts when enterprise content is ingested. Verify source integrity, classification, and authorization. During indexing, keep restricted or sensitive material out of searchable stores unless policy allows it. At retrieval, enforce the user's permissions, tenant isolation, and need to know. Then treat retrieved text as untrusted input because documents can carry prompt injections. Only after those checks should the model generate a response. Embeddings should be treated as sensitive data, not harmless math. A vector database can expose enterprise knowledge through retrieval, even when the original text is not visible. Controls need to follow the data, classify what is embedded, enforce access at query time, isolate tenants and business units, and encrypt every embedding workflow. Then, watch behavior. Unusual query volume, repeated probing, or cross-domain retrieval attempts can signal exfiltration. Ownership is usually shared across data, platform, and security teams. Model access should be managed like access to any sensitive enterprise platform. Internal models, cloud foundation models, and SaaS LLMs should pass through an approved model registry before use. That registry ties each model to allowed users, applications, environments, and data classifications. Provider policies define retention, training use, residency, and contractual limits. Telemetry then closes the loop by tracking cost, abnormal usage, security events, and audit evidence for compliance. Observability is the evidence layer for an AI system. Traditional logs show who accessed what, which APIs ran, and which data or models were touched. Telemetry adds the missing context: prompts, responses, retrievals, guardrail decisions, and model usage. When these events are centralized and correlated, teams can detect threats, investigate incidents, prove compliance, and improve controls. Because logs may contain sensitive content, they must be masked, encrypted, and tightly access controlled. Imagine a user trying to extract confidential data through a RAG chatbot. The prompt looks suspicious, and DLP detects sensitive content in the request, response, or retrieved context. SIM correlation adds identity, API, application, model, and data events to confirm the pattern. From there, SOAR can open a ticket, notify responders, collect evidence, and contain the blast radius by suspending access, limiting model use, or tightening retrieval permissions while the incident is investigated. Layer mapping gives structure to AI security. Identity protects people and machines. App and API controls defend entry points. AI and data controls govern models, RAG, and providers. Observability turns signals into action. Next, we use this map to prioritize risks, ownership, and investment.